Picture this. You're in a window seat somewhere over the North Atlantic. Dinner's been cleared. You've got your headphones in. And then the plane starts shaking. Not a little. Really shaking. The kind where the overhead bins rattle and the flight attendants grab the nearest armrest and sit down without being asked. And you do what every nervous flyer does. You look out the window at the wing. And the wing is moving, bending, flexing. The tip of it rising and falling in a way that your brain is absolutely not okay with. Because wings are metal. Metal doesn't bend. Except apparently it does right there in front of you, while you are inside the plane attached to the wing that is bending. Here's what's actually going on. That wing is not breaking. It is not damaged. It is not doing something unexpected. It is doing exactly what the engineers designed it to do. And the reason it's bending, the physics of why a flexible wing is dramatically safer than a rigid one, is one of the most counterintuitive things in all of aviation. Turbulence has never brought down a modern commercial aircraft. Not through wing failure. Not through loss of control. Not through any of the catastrophic scenarios your brain generates during a bumpy flight. And the reason it hasn't comes down to what that wing actually is, how it's built, what it's made of, and why the fact that it moves is the very thing keeping you safe. This is plainly put. Every Tuesday, we take something you've seen 1,000 times, pull it apart, and show you what's actually going on. If that's your kind of thing, subscribe right now and stay with us, because the most surprising part of this story is still ahead. Let's start with what turbulence actually is, because most people have the wrong mental model. The most common fear is that turbulence means the plane is dropping, that the air underneath it suddenly disappears and the aircraft falls into an empty pocket. That is not what happens. There are no empty pockets. Air is not thin enough, not patchy enough, not absent enough at 35,000 feet for the plane to simply fall through it. A better mental model, and pilots have used this analogy for decades, is a boat on a choppy sea. The water doesn't disappear under the hull. The hull just rides through irregular waves. The plane is not falling. It is riding through irregular air. So what is that irregular air? Turbulence comes from several different sources, and they behave very differently from each other. The kind most passengers are familiar with is convective turbulence, the kind associated with weather. Thunderstorms generate enormous columns of rising and falling air, and a plane flying near one will feel those columns as jarring bumps and drops. Pilots can see convective turbulence coming on radar. They route around it. It is dangerous if you fly into the heart of a severe thunderstorm, which commercial flights are not permitted to do, and it is manageable turbulence if you're flying near the edges of one. Then there is mountain wave turbulence, which happens when fast-moving air hits a mountain range and creates waves on the downwind side. Like a rock in a fast stream creates ripples that extend downstream. If you've ever had a particularly rough descent into Denver, Salt Lake City, or any city near a major mountain range, you've felt this. But the type of turbulence that gets less attention, and that is growing more common and more dangerous, is called clear air turbulence. And it is in a completely different category from the others. Clear air turbulence has no visual cues, no clouds, no weather radar signature, nothing that any instrument on the flight deck can reliably detect in advance. It comes from the jet stream, the high-altitude rivers of fast-moving air that circle the planet, and specifically from the places where two masses of air moving at different speeds rub against each other. That boundary creates chaotic, swirling motion. A plane flying through it has no warning. One moment the air is smooth. The next, the aircraft is being thrown in multiple directions simultaneously. This is the turbulence responsible for most of the injuries you see in aviation news. The Singapore Airlines flight in May 2024, a Boeing 777 on the London to Singapore route, encountered severe clear air turbulence over the Irrawaddy Basin in Myanmar at 37,000 feet. One passenger died from suspected cardiac arrest caused by the sudden forces. Dozens were injured. The plane experienced a rapid altitude change of thousands of feet in seconds, and it landed safely in Bangkok because the structure of the aircraft absorbed all of it without failing. That landing, and the fact that the plane held together, is worth understanding deeply, because it explains everything about how the wing is built. Here is the core engineering principle. If you build a wing that is completely rigid, that cannot flex at all, every force that hits it gets transmitted directly into the fuselage at full strength. Turbulence hits. The wing doesn't move. All of that energy goes straight into the joint where the wing meets the body of the plane. Do that thousands of times over the life of the aircraft, and that joint fatigues. Cracks propagate. The structure weakens at exactly the point where it can least afford to. Now build a wing that flexes. Turbulence hits. The wing bends upward. The energy is absorbed across the entire span of the wing rather than concentrated at the root. The fuselage feels a fraction of the original force. The wing returns to its normal position. No damage. No fatigue at the joint. The aircraft has essentially used the wing as a shock absorber for the whole plane. Think of a tree in a storm versus a telephone pole. The telephone pole is rigid. If the wind force exceeds its structural limit, it snaps. The tree bends. Branches move. The energy is distributed through the whole system. The tree survives winds that would break the pole. Aircraft wings are the tree. The materials make this possible in ways that weren't available even 20 years ago. Traditional aluminum wings could flex, but within limits. Aluminum fatigues over repeated stress cycles, which is why those wings required constant inspection and maintenance. Modern aircraft like the Boeing 787 Dreamliner and the Airbus A350 use carbon fiber reinforced polymer, composite material, for the wing structure. Carbon fiber composites are stronger than aluminum relative to their weight, and crucially, they do not fatigue the same way. They can handle repeated bending cycles over the life of the aircraft without the microscopic cracking that aluminum develops over time. The 787's wings are tested to deflect over 25 feet upward before reaching their breaking point, and that breaking point is required by certification standards to be at least 150% of the highest load the aircraft is ever expected to see in service. That 150% requirement is worth sitting with for a moment. Engineers calculate the absolute worst-case loads an aircraft could encounter in its entire operational life. The most severe turbulence, the most aggressive maneuver, the most extreme combination of weight and speed. Then they design the wing to handle 1.5 times that. The plane has to survive the worst possible day of flying and then survive it again, with half the margin still left over. The bending you see from your window seat, the tip of the wing rising several feet in moderate turbulence, is happening well within the normal operating range of the structure. Not the limit load, not the ultimate load. Normal. The wing is barely being exercised. Modern aircraft also have systems that actively reduce the loads turbulence puts on the wing. Both the 787 and A350 have gust load alleviation systems. Essentially, fly-by-wire computers that detect turbulence and automatically deflect control surfaces on the wings to counteract the forces before they fully propagate through the structure. The aircraft is not just passively absorbing turbulence. It is actively fighting back against it, adjusting hundreds of times per second through electronic control systems that are faster than any pilot input could ever be. So why does turbulence feel so alarming if the aircraft is handling it so comfortably? Because your body has no frame of reference for it. In a car on a bumpy road, you can see the road. You can see the bump coming. You brace. On a plane, the motion arrives without warning, without visible cause, without any way to anticipate it. Your vestibular system, the balance system in your inner ear, detects sudden acceleration and immediately tells your brain that something has gone wrong. The brain fills in the rest with worst-case scenarios because that is what brains do when they don't have complete information. But here is what the data actually says. Between 2009 and 2021, the FAA recorded 146 serious turbulence injuries across all commercial flights in the United States. In that same period, hundreds of millions of flights carried billions of passengers. The vast majority of turbulence injuries are caused by one thing: passengers not wearing their seatbelts. The aircraft held together in every single case. There is, however, a genuine challenge on the horizon. Severe clear air turbulence over the North Atlantic increased by 55% between 1979 and 2020, according to research from the University of Reading. The cause is climate change. Warming temperatures are strengthening the wind shear in the jet streams, creating more of the invisible turbulent boundaries that planes fly through without warning. By 2050, researchers estimate pilots may encounter twice as much severe clear air turbulence as they do today. The aircraft will handle it. The wings were built for this, and the margins built into those wings are far larger than anything the atmosphere is currently throwing at them. The engineering challenge is not the structure, it is detection. Building systems that can see clear air turbulence coming far enough in advance to give crews time to get the cabin secured. That is where aviation research is focused right now, from AI systems analyzing real-time atmospheric data to networks of commercial aircraft acting as airborne sensors, broadcasting turbulence data to every other plane in the region. The wing bending outside your window is not a warning. It is a demonstration. The most visible proof that the people who built your aircraft thought through exactly this moment: the shaking, the rattling, the alarming flex of a structure that most people assume should be rigid, and engineered their way through it before you ever boarded. The wing is supposed to do that. It always was. And that, plainly put, is what turbulence is actually doing to your airplane. Subscribe to Plainly Put. Every Tuesday we find something hiding in plain sight and show you what's really going on underneath it. Drop a comment and tell us what you want us to explain next.